Hello everyone, today's video is based on atoms and molecules, chapter 3, class 9. Before starting this video, please like and subscribe to my channel linked in Pharma. Let's start it. Introduction. Atoms and molecules form the fundamental building blocks of matter, playing a crucial role in shaping the physical world around us. The concept of atoms dates back to ancient times, with early Greek philosophers like Democritus proposing the idea of indivisible particles that make up all matter. However, it wasn't until the late 19th and early 20th centuries that the modern understanding of atoms and molecules began to take shape, thanks to groundbreaking work by scientists like John Dalton, Dmitry Mendeleev, and Albert Einstein. These pioneers paved the way for the development of atomic theory, the periodic table, and the recognition that molecules are composed of specific arrangements of atoms, each with its own unique properties and behavior. This brief overview highlights the historical journey that led to our contemporary comprehension of atoms and molecules, which underpins countless aspects of science, technology, and our everyday lives. Law of chemical combination. The laws of chemical combination, also known as the laws of stoichiometry, are fundamental principles that describe how different elements combine to form compounds and react with one another. These laws are essential for understanding the quantitative relationships in chemical reactions. There are three main laws of chemical combination. 1. Law of conservation of mass. 2. Law of definite proportions or law of constant composition. 3. Law of multiple proportions. These laws of chemical combination provide a foundation for understanding how elements interact, combine, and transform into different substances through chemical reactions. They have played a pivotal role in the development of modern chemistry and continue to guide our understanding of the principles governing chemical reactions and the composition of matter. Law of conservation of mass. The law of conservation of mass states that in any chemical reaction, the total mass of the reactants remains equal to the total mass of the products. In simpler terms, matter cannot be created or destroyed during a chemical process, it can only change from one form to another. This foundational principle, proposed by Antoine Lavoisier, underscores the idea that the total amount of material before and after a reaction remains constant, highlighting the preservation of mass in chemical transformations. Activity. Conservation of mass in a baking soda and vinegar reaction. Objective. To observe and demonstrate the law of conservation of mass using a simple chemical reaction. Materials. Baking soda, sodium bicarbonate, vinegar, acetic acid, balloon, funnel, measuring spoon, empty plastic bottle. Procedure. Preparation. Set up the activity in a well-ventilated area or outdoors to avoid inhaling the gases produced. Place the funnel in the mouth of the empty plastic bottle. Assembly. Using the measuring spoon, add a small amount of baking soda to the balloon. This will serve as the reactant. Carefully attach the neck of the balloon to the open end of the funnel, ensuring it is securely fastened but not inflated. Reaction. Lift the balloon to allow the baking soda to fall into the plastic bottle. Using the funnel, pour vinegar into the plastic bottle containing the baking soda. The vinegar will react with the baking soda, producing carbon dioxide gas and water. Observation. As the reaction occurs, the balloon will begin to inflate due to the carbon dioxide gas being produced. The balloon inflates because the gas cannot escape from the bottle, so it fills the balloon. Analysis. Observe the changes in the size of the balloon and the contents of the plastic bottle. After the reaction has completed and the balloon has stopped inflating, carefully remove the balloon from the plastic bottle without letting any gas escape. Discussion. Discuss the observations and ask participants what they think happened during the reaction. Emphasize that even though the balloon inflated, the total mass of the substances, baking soda, vinegar, and the gases produced, remained constant throughout the reaction. Relate this to the law of conservation of mass by explaining that the mass of the reactants, baking soda and vinegar, is equal to the mass of the products, carbon dioxide gas and water, formed during the reaction. Conclusion. Through this activity, participants can visually witness a chemical reaction while observing that the total mass of the reactants and products remains the same. This serves as a tangible demonstration of the law of conservation of mass and reinforces the concept that matter is neither created nor destroyed during chemical reactions. Law of definite proportions, or law of constant composition. The law of definite proportions, also known as the law of constant composition, states that a chemical compound always contains the same elements in fixed and definite proportions by mass, regardless of the source or method of preparation. In other words, the relative masses of the elements in a compound remain constant, ensuring consistent composition regardless of variations in how the compound is produced. This law was formulated by Joseph Proust and underscores the predictable nature of compound formation, serving as a foundational principle in chemistry. Activity: investigating the composition of water. Objective: to demonstrate the law of definite proportions using the example of water. Materials: hydrogen gas, oxygen gas, empty syringes or gas collection tubes, ignition source. Examples: matches or a lighter, balance or scale, if available, safety goggles. Procedure: preparation: set up the activity in a safe and well-ventilated area. Ensure participants wear safety goggles to protect their eyes. Collection of gases: collect a known volume of hydrogen gas in one syringe or gas collection tube. Collect a known volume of oxygen gas in another syringe or gas collection tube. Combustion reaction: attach the syringe or tube containing hydrogen gas to one end of a long, thin tube. Attach the syringe or tube containing oxygen gas to the other end of the tube. Ensure the tubes are well sealed to prevent gas leaks. Ignite the mixture of hydrogen and oxygen gases at the center of the tube using an ignition source. Observation: as the gases react, water vapor will form in the tube. The reaction can be accompanied by a pop sound due to the rapid formation of water vapor. Analysis: measure the mass of the water vapor produced after the reaction, if possible. Discuss the composition of water and the relative masses of hydrogen and oxygen that combine to form it. Emphasize that the mass ratio of hydrogen to oxygen in water is always approximately 1:8 by mass, regardless of the source of hydrogen and oxygen gases. Discussion: relate the observations to the law of definite proportions. Highlight that the ratio of the masses of hydrogen and oxygen in water is consistent and fixed, regardless of the origin of the gases or the method of preparation. Conclusion: through this activity, participants can visually observe the formation of water through the reaction of hydrogen and oxygen gases. By measuring the mass of the water vapor produced and discussing the consistent ratio of hydrogen and oxygen in water, participants can understand and appreciate the concept of the law of definite proportions, which states that compounds have fixed and unchanging ratios of elements by mass. Dalton's atomic theory, formulated by the English chemist and physicist John Dalton in the early 19th century, was a groundbreaking framework that provided a comprehensive explanation for the behavior and characteristics of matter. The theory marked a significant step in the development of modern atomic theory and laid the foundation for our understanding of the fundamental nature of atoms and their interactions. Here's an explanation of Dalton's atomic theory. Dalton's atomic theory. Elements consist of indivisible atoms. Dalton proposed that all matter is composed of tiny, indivisible particles called atoms. Atoms are the fundamental building blocks of elements and cannot be further divided or broken down by chemical means. Atoms of the same element are identical. According to Dalton's theory, atoms of a given element are identical in size, mass, and chemical properties. This concept was later refined with the discovery of isotopes, which are atoms of the same element with different numbers of neutrons and thus different masses. Atoms of different elements differ. Atoms of different elements have distinct properties and characteristics. They vary in terms of size, mass, and chemical behavior. Dalton's theory proposed that the unique properties of elements are a result of the different arrangements of atoms. Atoms combine in whole number ratios. Dalton suggested that atoms combine with one another to form compounds in simple, whole number ratios. This was based on observations of chemical reactions and the ratios of elements present in different compounds. Chemical reactions involve atom rearrangement. Dalton's theory emphasized that chemical reactions are a result of the rearrangement of atoms. During a chemical reaction, atoms are neither created nor destroyed, they are rearranged to form new compounds. Significance and contributions. Dalton's atomic theory marked a shift from the earlier notion of matter being continuous and undividable to the idea of matter being composed of discrete, indivisible particles. The theory provided a unifying explanation for the laws of chemical combination and paved the way for a more systematic understanding of chemical reactions. It also laid the groundwork for the development of the periodic table, which organizes elements based on their atomic properties. While Dalton's atomic theory has been refined and expanded upon with the advancement of scientific knowledge, it remains a cornerstone of modern chemistry. Subsequent discoveries, such as the existence of subatomic particles, electrons, protons, neutrons, and the wave-particle duality of matter, have added depth to our understanding of atomic structure. Nonetheless, Dalton's theory remains an essential historical milestone in the journey toward comprehending the nature of matter at its most fundamental level. What is an atom? An atom is the smallest unit of matter that retains the properties of an element. It is the basic building block of all matter in the universe. Atoms are incredibly tiny and consist of even smaller subatomic particles, which include protons, neutrons, and electrons. Here's a breakdown of these components. 1. Protons. Protons are positively charged subatomic particles found in the nucleus, central core, of an atom. They contribute to the atom's mass and determine its identity as a specific element. The number of protons in the nucleus is called the atomic number, which uniquely identifies each element on the periodic table. 2. Neutrons. Neutrons are subatomic particles that have no charge, meaning they are electrically neutral. Neutrons also reside in the nucleus alongside protons. They add to the mass of the atom but do not significantly influence its chemical properties. The number of neutrons can vary within an element, giving rise to different isotopes of that element. 3. Electrons. Electrons are negatively charged subatomic particles that orbit the nucleus in energy levels called electron shells or orbitals. Electrons are much smaller in mass compared to protons and neutrons but play a crucial role in determining the chemical behavior and bonding of atoms. The structure of an atom resembles a miniature solar system, with the nucleus at the center analogous to the Sun and the electrons orbiting around it like planets. However, this model is a simplification, and the behavior of electrons is better described by the principles of quantum mechanics, which account for their wave-like nature and the uncertainty of their exact positions. Atoms of different elements have varying numbers of protons in their nuclei, giving rise to their distinct properties. For example, an atom with 1 proton is hydrogen, while an atom with 6 protons is carbon. The combinations of different elements in various proportions form molecules and compounds, which are the basis of all substances. In summary, atoms are the fundamental units of matter composed of protons, neutrons, and electrons. They are the building blocks of elements and play a central role in the composition, structure, and behavior of all materials in the universe. How big are atoms? Atoms are incredibly small, with sizes on the order of angstroms or picometers. The size of an atom can vary depending on the specific element and its electronic configuration. Here are a few ways to visualize the size of atoms. 1. Atomic radius. The atomic radius is a measure of the size of an atom. It is defined as half the distance between the nuclei of two adjacent atoms in a molecule or crystal lattice. Atomic radii are typically reported in picometers, pm. For example, the atomic radius of hydrogen is about 25 pm, while the atomic radius of an atom like cesium can be around 265 pm. 2. Comparisons. To put the size of an atom in perspective, consider that if an atom were magnified to the size of a football stadium, the nucleus would be roughly the size of a pea placed at the center of the stadium, and the electrons would be like specks orbiting the outer edges of the stadium. 3. Visualization techniques. Advanced microscopy techniques, such as scanning tunneling microscopy and atomic force microscopy, have made it possible to see individual atoms. These techniques use tiny probes to interact with the atoms on surfaces, allowing researchers to create images with atomic scale resolution. 4. Relative size. Atoms are so small that they are beyond the limit of direct observation using visible light or even optical microscopes. Their size is comparable to the wavelengths of X-rays, which is why techniques like X-ray crystallography are used to determine the arrangement of atoms in molecules. In terms of scale, a typical atomic radius is on the order of 0.1 to 0.3 nanometers, which is equivalent to 1 to 3 angstroms, or around 100 to 300 picometers. To grasp the minute scale of atoms, it's helpful to consider that there are about 10 million picometers in a millimeter and that even the tip of a fine needle contains billions of atoms. What are the modern-day symbols of atoms of different elements? The modern symbols of atoms are represented using chemical symbols, which are shorthand notations for the elements. Each element is denoted by a 1 or 2 letter symbol, typically derived from the element's name in English, Latin, or another language. These symbols are universally recognized in the field of chemistry and are used to represent atoms of different elements. Here are some examples of modern chemical symbols for elements. Hydrogen, H, helium, Ha, carbon, C, oxygen, O, nitrogen, N, sodium, Na, magnesium, Mg, aluminum, Al, silicon, Si, chlorine, Cl, iron, Fa, copper, Cu, gold, Au, silver, Ag, lead, Pb, uranium, U. The first letter of the chemical symbol is always capitalized, and if the symbol consists of 2 letters, the second letter is in lowercase. These symbols are used to represent individual atoms of elements in chemical equations, formulas, and other notations. In addition to the 1 and 2 letter chemical symbols, elements are often accompanied by their atomic number, Z, and atomic mass, usually given as the atomic mass unit in the periodic table. This information provides a more comprehensive understanding of each element's properties and characteristics. The use of chemical symbols is a fundamental part of chemical communication and allows scientists to convey complex information about elements and compounds in a concise and standardized manner. Atomic mass. Atomic mass refers to the mass of an atom, which is typically measured in atomic mass units or unified atomic mass units. It is a measure of the total mass of the particles that make up an atom, including protons, neutrons, and electrons. The atomic mass is an important concept in chemistry and physics, as it helps in understanding the relative masses of different elements and their isotopes. Here are a few key points to understand about atomic mass. 1. Protons and neutrons contribution. The majority of an atom's mass comes from its protons and neutrons, which are concentrated in the nucleus. Electrons, due to their much smaller mass, contribute only a tiny fraction to the overall atomic mass. 2. Isotopes and atomic mass. Most elements have multiple isotopes, which are atoms with the same number of protons but different numbers of neutrons. Since isotopes of an element have different atomic masses, the atomic mass reported on the periodic table is often an average of the atomic masses of its naturally occurring isotopes, weighted by their abundances. 3. Atomic mass unit. The atomic mass unit is a unit of mass used to express atomic and molecular weights. It is defined as 1/12 the mass of a carbon-12 atom. Therefore, the atomic mass of carbon-12 is exactly 12 atomic mass units. 4. Unified atomic mass unit. In recent years, the unified atomic mass unit has been used interchangeably with the atomic mass unit. The unified atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom and is approximately equal to 1.660539066660 multiplied by 10 to the power 27 kg. 5. Atomic mass on the periodic table. The atomic mass of an element is usually listed in the periodic table beneath the element's symbol. It can be a decimal value because it's an average of the atomic masses of the isotopes. This value is sometimes referred to as the relative atomic mass or atomic weight. 6. Calculating molecular mass. Atomic mass is also used to calculate the molecular mass of a compound. It involves adding up the atomic masses of the constituent atoms in a molecule, as indicated by the molecular formula. In summary, atomic mass is a measure of the total mass of an atom, considering its protons, neutrons, and electrons. It is an important concept in chemistry for understanding the composition of elements and compounds. Here are the approximate atomic masses, in unified atomic mass units, U, of a few elements commonly found in nature. Hydrogen, H, 1.008 U. Helium, Ha, 4.0026 U. Carbon, C, 12.011 U. Oxygen, O, 15.999 U. Nitrogen, N, 14.007 U. Sodium, Na, 22.990 U. Magnesium, Mg, 24.305 U. Aluminum, Al, 26.982 U. Silicon, Si, 28.085 U. Chlorine, Cl, 35.453 U. Iron, Fa, 55.845 U. Copper, Cu, 63.546 U. Gold, Au, 196.966 U. Silver, Ag, 107.868 U. Lead, Pb, 207.2 U. Uranium, U, 238.029 U. Keep in mind that these values are approximate and may vary slightly due to the presence of isotopes. Isotopes are atoms of the same element with different numbers of neutrons and therefore slightly different atomic masses. The values provided here are based on the average atomic masses of the naturally occurring isotopes of each element. How do atoms exist? Atoms exist as stable particles due to the balance between the attractive and repulsive forces that act within their structure. The fundamental particles that make up an atom, protons, neutrons, and electrons, are held together by the interactions between electromagnetic forces, gravitational forces, and quantum mechanical effects. Here's a more detailed explanation of how atoms exist. 1. Protons and neutrons in the nucleus. Protons and neutrons are located in the nucleus at the center of the atom. Protons have a positive electric charge, while neutrons have no electric charge, they are electrically neutral. The strong nuclear force is responsible for binding protons and neutrons together in the nucleus. This force is stronger than the electromagnetic repulsion between positively charged protons. 2. Electrons in orbitals. Electrons are negatively charged particles that orbit the nucleus in energy levels called electron shells or orbitals. Electromagnetic forces attract electrons to the positively charged nucleus. However, the electrons are also subject to their own kinetic energy and quantum mechanical effects, which lead to their distribution in specific orbitals. 3. Quantum mechanical effects. The behavior of electrons as described by quantum mechanics, a branch of physics that deals with the behavior of particles at the atomic and subatomic scale. Quantum mechanics introduces the concept of probability distributions for electron positions, and electron orbitals are regions of space where an electron is likely to be found with a high probability. 4. Electromagnetic force instability. The electromagnetic force between electrons and the nucleus is balanced by the centrifugal force of electrons in their orbits. This balance of forces allows atoms to remain stable and prevents electrons from collapsing into the nucleus. 5. Stable and unstable atoms. Stable atoms have balanced forces that result in a relatively long lifetime. The most stable atoms have complete electron shells, which confer high stability. Unstable atoms, known as radioactive isotopes, may undergo decay over time due to an imbalance in the forces within the nucleus. 6. Nuclear reactions. Under specific conditions, atoms can undergo nuclear reactions that involve changes in the number of protons and neutrons in the nucleus. These reactions release or absorb energy and can result in the formation of different elements. In summary, atoms exist due to a delicate balance of electromagnetic forces, gravitational forces, and quantum mechanical effects that govern the interactions between protons, neutrons, and electrons. This balance of forces and the principles of quantum mechanics give rise to the stable structure of atoms and the diversity of elements in the universe. What is a molecule? A molecule is a group of two or more atoms that are chemically bonded together. These atoms can be of the same element or different elements. Molecules are the fundamental units of chemical compounds and are formed through chemical reactions where atoms share or exchange electrons to achieve a more stable electron configuration. Here are a few key points about molecules. 1. Chemical bonding. Molecules are held together by chemical bonds, which result from the sharing, donating, or receiving of electrons between atoms. The type of bonding, whether covalent, ionic, or metallic, determines the properties of the molecule. 2. Covalent molecules. In covalent molecules, atoms share electrons to achieve a more stable electron configuration. This type of bonding occurs between nonmetals and results in the formation of molecules with discrete structures. 3. Ionic compounds. While not strictly called molecules, ionic compounds consist of positively and negatively charged ions that are held together by electrostatic forces. They form when electrons are transferred from one atom to another, leading to the creation of ions. 4. Structural diversity. Molecules can vary greatly in size, complexity, and structure. They can be simple diatomic molecules, examples, O2, H2, or complex macromolecules, examples, proteins, DNA. 5. Chemical properties. Molecules have their own unique chemical properties and reactivity. The arrangement of atoms and the types of bonds present influence how a molecule interacts with other molecules in chemical reactions. 6. Physical properties. Molecules' physical properties, such as melting and boiling points, solubility, and conductivity, are influenced by their chemical composition and structure. 7. Examples. Some common examples of molecules include water, composed of 2 hydrogen atoms and 1 oxygen atom bonded covalently. Carbon dioxide, composed of 1 carbon atom and 2 oxygen atoms bonded covalently. Methane, composed of 1 carbon atom and 4 hydrogen atoms bonded covalently. 8. Representation. Molecules are often represented using molecular formulas, which provide information about the types and numbers of atoms in the molecule. Structural formulas and three-dimensional models can also be used to represent the arrangement of atoms in a molecule. In summary, a molecule is a group of atoms that are held together by chemical bonds. Molecules play a central role in the composition and behavior of matter, and understanding their properties and interactions is fundamental to the field of chemistry. Molecules of elements. Molecules of elements exist for certain elements, typically those that naturally occur as diatomic molecules. Diatomic molecules are molecules composed of 2 atoms of the same element bonded together. These molecules are stabilized by covalent bonds, where atoms share electrons to achieve a more stable electron configuration. Here are a few examples of diatomic molecules of elements. Hydrogen. Hydrogen gas consists of 2 hydrogen atoms, H, bonded together. Nitrogen. Nitrogen gas consists of 2 nitrogen atoms, N, bonded together. Oxygen. Oxygen gas consists of 2 oxygen atoms bonded together. Fluorine. Fluorine gas consists of 2 fluorine atoms bonded together. Chlorine. Chlorine gas consists of 2 chlorine atoms bonded together. Bromine. Bromine is a liquid composed of diatomic bromine molecules. Iodine. Iodine is a solid composed of diatomic iodine molecules. These diatomic molecules are stable because the atoms share electrons, resulting in a more complete outer electron shell for each atom. This sharing of electrons allows the atoms to achieve a stable electron configuration similar to that of noble gases, making the molecules relatively unreactive under normal conditions. It's important to note that not all elements naturally form diatomic molecules in their standard state. Elements like helium, neon, argon, and others have full valence electron shells and do not typically form stable diatomic molecules. Molecules of compounds. Molecules of compounds are formed when atoms of different elements chemically bond together. These bonds result from the sharing, donating, or receiving of electrons, leading to the formation of distinct chemical substances with unique properties. Here are a few examples of molecules of compounds. Water. Water is a compound composed of two hydrogen atoms, H, and one oxygen atom, O, bonded together. The oxygen atom forms covalent bonds with two hydrogen atoms, resulting in a bent molecular shape. Carbon dioxide. Carbon dioxide is a compound composed of one carbon atom, C, and two oxygen atoms, O, bonded together. The linear molecular shape is due to the arrangement of the atoms and the double bonds between carbon and oxygen. Methane. Methane is a compound composed of one carbon atom, C, and four hydrogen atoms, H, bonded together. The carbon atom forms single covalent bonds with four hydrogen atoms, resulting in a tetrahedral molecular shape. Table salt. Sodium chloride. Sodium chloride is a compound composed of one sodium atom and one chlorine atom bonded together through an ionic bond. Sodium donates an electron to chlorine, resulting in the formation of positively charged sodium ions and negatively charged chloride ions that are attracted to each other. Glucose. Glucose is a compound composed of 6 carbon atoms, C, 12 hydrogen atoms, H, and 6 oxygen atoms, O, bonded together in a complex arrangement. The molecular structure of glucose is more intricate and involves various covalent bonds between carbon, hydrogen, and oxygen atoms. These are just a few examples of molecules of compounds. Compounds can vary greatly in complexity, structure, and properties, depending on the types and arrangements of atoms involved. The way atoms are bonded within a compound determines its chemical and physical characteristics. What is an ion? An ion is an electrically charged particle that forms when an atom gains or loses electrons. Ions can be either positively charged, known as cations, or negatively charged, known as anions, depending on whether they have lost or gained electrons compared to their neutral state. Ions play a crucial role in chemical reactions, electrical conductivity, and various biological processes. Here's a more detailed explanation of ions. Cations. Cations are formed when an atom loses one or more electrons. This results in an excess of positive charge, as the number of positively charged protons in the nucleus remains unchanged, but there are now fewer negatively charged electrons to balance the charge. Common examples of cations include metal ions like sodium and calcium. These ions are often created when metals lose electrons to achieve a stable electron configuration similar to that of a noble gas. Anions. Anions are formed when an atom gains one or more electrons. This results in an excess of negative charge, as the number of negatively charged electrons in the atom now exceeds the number of positively charged protons in the nucleus. Common examples of anions include chloride and oxide. Chloride forms when chlorine gains an electron, while oxide forms when oxygen gains 2 electrons. Ionic compounds. Ions play a significant role in forming ionic compounds. Ionic compounds result from the strong electrostatic attraction between positively charged cations and negatively charged anions. In an ionic compound like sodium chloride, sodium donates an electron to chlorine, resulting in the formation of a sodium cation and a chloride anion. The attractive force between these oppositely charged ions holds the compound together. Electrical conductivity. Ions in solution or in a molten state can conduct electricity because they can move in response to an electric field. This is why solutions of ionic compounds are good conductors of electricity. Biological significance. Ions are vital in biological systems, as they play roles in nerve impulses, muscle contractions, and other physiological processes. Sodium, potassium, calcium, and other ions are critical for maintaining proper cellular function. Ionic compounds are formed through the combination of positively charged ions, cations, and negatively charged ions, anions. These compounds are held together by strong electrostatic forces of attraction between the oppositely charged ions. Here are a few examples of ionic compounds. Sodium chloride. Sodium chloride, commonly known as table salt, is composed of sodium cations and chloride anions. The strong ionic bonds between sodium and chloride ions give salt its characteristic properties. Potassium nitrate. Potassium nitrate, often used in fertilizer and food preservation, consists of potassium cations and nitrate anions. The nitrate ion is composed of one nitrogen atom and three oxygen atoms, carrying a net negative charge. Calcium carbonate. Calcium carbonate is found in minerals like limestone, marble, and chalk. It contains calcium cations and carbonate anions. The carbonate ion consists of one carbon atom and three oxygen atoms, carrying a net negative charge. Magnesium oxide. Magnesium oxide is an ionic compound formed by the combination of magnesium cations and oxide anions. Mg2 plus O2 minus. The oxide ion consists of two oxygen atoms, each carrying a charge of -1. Writing chemical formulae. Writing chemical formulas involves using symbols and subscripts to represent the elements and the number of atoms in a compound. Chemical formulas provide a concise way to represent the composition of a substance. Here's how to write chemical formulas. Identify the elements. Determine which elements are present in the compound. Each element is represented by its chemical symbol, example, H for hydrogen, O for oxygen, Na for sodium. Determine the subscripts. Subscripts indicate the number of atoms of each element in the compound. These numbers are written as small, lower digits to the right of the element's symbol. If no subscript is written, it's assumed to be 1. Use parentheses. Parentheses are used when there are multiple atoms of a specific element. The subscript outside the parentheses applies to all the atoms within the parentheses. Pay attention to charges. For ions and ionic compounds, charges are indicated as superscripts. Positive charges, cations, are written with a plus sign, plus, and negative charges, anions, are written with a minus sign minus. Here are some examples of writing chemical formulas. Water. Hydrogen has 2 atoms, so the subscript is 2. Oxygen has 1 atom, so the subscript is 1, though it's often omitted. Sodium chloride. Sodium is a cation with a charge of +1. Chlorine is an anion with a charge of -1. The charges balance, so no subscripts are needed. Carbon dioxide. Carbon has 1 atom. Oxygen has 2 atoms, so the subscript is 2. Calcium carbonate. Calcium is a cation with a charge of +2. Carbon has 1 atom. Oxygen has 3 atoms, so the subscript is 3. Parentheses are used around the carbonate ion to indicate that there are 3 oxygen atoms. Ammonium nitrate. Ammonium consists of 1 nitrogen and 4 hydrogen atoms. Nitrate consists of 1 nitrogen and 3 oxygen atoms. Parentheses are used around ammonium to indicate the entire ion. Remember that correctly representing the number of atoms and charges is essential for accurately depicting compounds. Additionally, understanding the valence of elements and the rules for writing chemical formulas is crucial for creating accurate representations of substances. Formulae of simple compounds. Here are the chemical formulas of some simple compounds. Water. Chemical formula, H2O. Carbon dioxide. Chemical formula, CO2. Sodium chloride, table salt. Chemical formula, NaCl. Ammonia. Chemical formula, NH3. Methane. Chemical formula, CH4. Hydrogen peroxide. Chemical formula, H2O2. Carbon monoxide. Chemical formula, CO. Sulfuric acid. Chemical formula, H2SO4. Nitric acid. Chemical formula, HNO3. Table sugar, sucrose. Chemical formula, C12H22O11. Calcium carbonate, limestone. Chemical formula, CaCO3. Hydrogen sulfide. Chemical formula, H2S. These are just a few examples of simple compounds along with their chemical formulas and names. Understanding the chemical formulas of compounds is essential for representing their composition and for communicating their properties and behavior in various chemical reactions. Molecular mass. Molecular mass, also known as molecular weight, is the sum of the atomic masses of all the atoms in a molecule. It is expressed in atomic mass units or unified atomic mass units. Molecular mass is a crucial concept in chemistry as it helps to quantify the amount of substance and to perform various calculations involving compounds. Here's how to calculate molecular mass. Identify the elements. Determine which elements are present in the molecule and their respective atomic masses. The atomic masses can be found on the periodic table. Count the atoms. Count the number of atoms of each element in the molecule. Calculate the molecular mass. Multiply the atomic mass of each element by the number of atoms of that element in the molecule. Then, sum up the results for all elements. Units. The molecular mass is expressed in atomic mass units or unified atomic mass units. These units are defined relative to the mass of a carbon-12 atom. Here's an example calculation of the molecular mass of water. Hydrogen. Atomic mass equals 1.008 atomic mass units. Oxygen. Atomic mass equals 15.999 atomic mass units. Molecular mass of water equals 2 multiplied by atomic mass of hydrogen plus atomic mass of oxygen equals 2 multiplied by 1.008 atomic mass units plus 15.999 atomic mass units equals 2.016 atomic mass units plus 15.999 atomic mass units equals 18.015 mol. So, the molecular mass of water is approximately 18.015 atomic mass units. Molecular mass is used in various calculations, such as determining the amount of substance, moles, in a given mass of a compound, calculating the percent composition of elements in a compound, and predicting the outcomes of chemical reactions. It provides a quantitative basis for understanding the composition and behavior of substances at the molecular level. Formula unit mass. Formula unit mass, also known as formula mass or formula weight, is the sum of the atomic masses of all the atoms in the empirical formula of an ionic compound. It is used for ionic compounds because they do not exist as discrete molecules like covalent compounds. Instead, ionic compounds are composed of repeating units of positive and negative ions arranged in a three-dimensional lattice structure. Formula unit mass is expressed in atomic mass units or unified atomic mass units. Here's how to calculate formula unit mass for an ionic compound. Identify the ions. Determine the types of ions present in the compound, both cations, positively charged ions, and anions, negatively charged ions. You'll need their respective charges and atomic masses. Determine the empirical formula. The empirical formula represents the simplest whole number ratio of ions in the compound. For example, for sodium chloride, the empirical formula is sodium chloride. Calculate the formula unit mass, multiply the absolute value of the charge of each ion by the number of ions of that type in the empirical formula. Then, sum up the results for all ions. Here's an example calculation for the formula unit mass of sodium chloride. Sodium. Atomic mass equals 22.990 atomic mass units. Chlorine. Atomic mass equals 35.453 atomic mass units. Empirical formula of sodium chloride, 1 sodium ion and 1 chloride ion. Formula unit mass of sodium chloride equals charge of sodium ion multiplied by atomic mass of sodium plus charge of chloride ion multiplied by atomic mass of chloride equals 1 multiplied by 22.990 atomic mass units plus 1 multiplied by 35.453 atomic mass units equals 22.990 atomic mass units plus 35.453 atomic mass units equals 58.443 atomic mass units. So, the formula unit mass of sodium chloride is approximately 58.443 atomic mass units. Formula unit mass is used to quantify the mass of a representative unit of an ionic compound. It's important for stoichiometry calculations and for understanding the properties and behavior of ionic compounds in various contexts. Thank you for watching. Please like, share and subscribe to my channel LinkedIn Pharma.